Welcome back. This is part 3. So far, across the first two parts, we have built a single server with a database, an index, a cache, and a CDN, and it works nicely. But this part asks the big question: what happens when one of everything is not enough? When millions of people arrive at once? This whole part is about scaling, load balancer, statelessness, replication, sharding, and famous cap theorem. Let's begin. Okay, our store is getting popular, thousands of people at once, and our one server is struggling. It simply cannot answer everyone fast enough. So we need to grow, and there are exactly two ways to grow, and knowing the difference well is interview basics. The first way is vertical scaling, also called scaling up. This just means make the one machine bigger, more CPU, more memory, a faster disk. And honestly, it is the simplest fix. You change nothing about your code, you just rent a stronger machine. And it has two hard limits. One, there is a ceiling. You cannot buy an infinitely powerful computer, so eventually you run out of bigger. And two, and this is a serious one, it is still just one machine. So if it fails, your entire site goes down. We call that a single point of failure. One thing whose failure takes everything with it. The second way is horizontal scaling, scaling out. Instead of one bigger machine, you run many ordinary machines, all doing the same job, sharing the load between them. And this is powerful for two reasons. One, there is basically no ceiling. You need more capacity, you add more machines. And two, there is no single point of failure at the app server layer. If one machine dies, the others keep serving, and users do not even notice. The catch is that it is more complex. Now you have many machines and you need something to spread the traffic across them, and they cannot each keep their own private memory of users. And solving those two problems is literally the next two concepts. So in our store, we choose horizontal scaling. Many servers, no ceiling, no single point of failure. But the moment you have many servers, you hit an obvious question. When a request comes in, which server should handle it? And the answer to that is one of the most famous components in all of the system design, the load balancer. Okay, we now have, let's say, 10 identical servers, but the user's browser only knows one address. So something has to sit in front, receive every request, and decide which of the 10 servers should handle it. That something is a load balancer, and it is one of the most important pieces in any large system. At high level, one front door, one public address, hiding a whole group of servers behind it, and spreading the requests evenly across them. Now, how does it decide which server? There are a few standard methods and you should know them by name. The simplest is round robin. Just go in turn. Server 1, server 2, server 3. Go back to 1. Next is least connections. Send the request to whichever server is currently least busy, which is smarter when some requests take longer. And there is IP hash. Use the user's address to always send the same user to the same server. And that has a name, a sticky session, sending a user back to the server that already knows them. It works, but as we'll see in a moment, the cleaner way is to keep servers stateless instead. And finally, you can add weights to send more traffic to your more powerful machines. And here is a critical job of the load balancer, health checks. The load balancer constantly pings each server behind it, asking, are you alive and healthy? And the moment a server stops responding, the load balancer stops sending it traffic. It routes around the dead one automatically. This is exactly what gives us that no single point of failure we wanted from horizontal scaling. So, in practice, you never just run one, you run at least two, and the traffic is pointed at whichever one is healthy. One server dies, the load balancer quietly skips it. User notice nothing. One more distinction for the interview, load balancers come in at two levels. A L4 load balancer works at the transport level. It only looks at IP addresses and ports, so it is very fast, but not very smart. An L7 load balancer works at the application level. It can actually read the request, the path, the headers, so it can do smart routing, like sending slash images to one group of servers and slash checkout to another. L4 is fast, L7 is smart. And quickly, you will hear three related words that confuse people: reverse proxy, load balancer, and API gateway. They are all front door components, and honestly, they overlap. A reverse proxy is the general receptionist in front of your servers. A load balancer specifically spreads load. And an API gateway, which we will meet later, adds smart features like authentication and rate limiting for many services. Same family, different focus. So, in our store, the load balancer is single address that the world talks to, quietly spreading every request across our fleet of servers and skipping any that die. But this creates a subtle new problem. If your requests are landing on different servers each time, how does any one server remember that you are logged in? And that is our next concept, statelessness. Okay, so remember, HTTP is stateless. The server does not automatically remember you. And now it is worse because with a load balancer, your first request goes to server A and your next one might be going to server B, a completely different machine that has never seen you, right? So, if server A stored this user is logged in its own memory, server B has no idea. So, how does the store remember you across requests and across servers? First, the golden rule and a very common interview point. Your servers should be stateless, meaning no server keeps any personal per user memory of its own. Why? Because if any server can be handling any user at any time, none of them can rely on private memory. And the big benefit is that this makes your servers interchangeable. You can add, remove, or restart any of them freely, which is exactly what makes horizontal scaling work. So, the state, your login, your cart must live somewhere shared, not inside one server. So, where does it live? It starts with a cookie. A cookie is just a small piece of data that server gives your browser, and your browser automatically sends it back on every future request. So, the server can put a little identifier in a cookie, and now every request carries that identifier. And there are two main ways to use it. The first way is server side sessions. When you log in, the server creates a session, the record that says this ID belongs to this logged in user, and stores it in a shared place that all servers can reach, like a Redis store. It gives your browser just the session ID in a cookie. Now, on every request, any server reads that ID, looks it up in the shared session, and knows who you are. The benefit, you can instantly cancel a session like a logout. The cost, every request needs that extra lookup. The second way is a JWT, a JSON Web Token. Here, instead of storing a session on the server gives your browser a signed token that already contains your identity, like user42 logged in, with a cryptographic signature that proves the server created it and nobody tampered with it. And how does that signature actually work? Our servers share one secret key that only they know. The server takes the contents of the token, mixes them with that secret, and runs the whole thing through a one way scrambling function. And the result is the signature stuck on the end. So, when any of our servers receives the token back, it does the exact same calculation itself and compares. If even one character of that contents was changed, the result will not match and the token is rejected. So, our servers share one small secret key instead of one big session store. And one important point to get right, the token is readable by anyone who has it. The signature only stops it being forged, it does not hide what is inside. So, you never put secrets in it. So, now any server can just verify the signature and trust the token. No lookup, no shared store needed. The benefit, it scales beautifully. No database hit. The cost, it is harder to cancel early because the token is valid until it expires. Sessions versus tokens, lookup but revocable versus no lookup but hard to revoke. This is the classic trade off between the two. So, in our store, statelessness plus a shared session store or a JWT is what lets any of our many servers recognize you, no matter which one you land on. Now, we have scaled our servers out nicely, but all of those servers are still talking to one database, and that is now the bottleneck. So, the next few concepts are all about scaling the database itself, starting with replication. Okay, we have many servers now, but they are all reading and writing to a single database, and that is a two problems at once. One, that single database is now a bottleneck and a single point of failure. If it dies, the whole store dies. And two, it can only handle so many reads per second, so we need more than one copy of the database. And the first technique for that is replication. Replication means keeping multiple copies of the database in sync. The standard setup, and know these words, is a leader and follower, sometimes called primary and replica. There is one leader, and it is the only one that accepts writes, creating orders, updating stock. And there are one or more followers, which are copies of the leader, and they handle reads. And how does that copying actually happen? The leader writes every single change it makes into an ordered log. Insert this row, update that one in order, and each follower stays connected to the leader, reads that log as it grows, and applies the exact same changes in the exact same order. So a follower is not guessing, it is replaying the leader's history. And this buys us two things. One, we can now handle far more reads because we can add many read replicas and spread all the read traffic across them, while the leader focuses on writes. Most applications read far more than they write, so this is huge. And 2, if the leader dies, we can promote one of the followers to be the new leader. This is called a failover. So the database is no longer a single point of failure. And that promotion is not a person doing it in the middle of the night. The machines watch each other, and when enough of them agree the leader is gone, they vote on which follower takes over. And the reason they vote instead of any one mission deciding is to avoid ending up with two leaders accepting rights at once, which is a genuinely bad situation. But there is one catch that matters a lot in practice, so understand it well. How the copying happens matters. In asynchronous replication, the leader confirms your rights immediately and copies to the followers a moment later. This is fast, but it means the followers can be slightly behind. We call this replication lag, and it causes a classic bug. You update your profile photo, the write goes to the leader, but your very next read happens to hit a follower that has not caught up yet. So you see your old photo. This is called the read your own writes problem. The alternate, synchronous replication. Wait for the followers before confirming. So no lag, but slower writes. Fast but stale or slow but fresh. That trade off is the whole thing. And one more real risk with asynchronous replication, if the leader dies before it has copied its last few writes to the followers, those writes which it already confirmed to the user can simply be lost in the failover. So, failover is not entirely free either. So, in our store, replication lets us handle a huge amount of read traffic and survive a database failure. And one thing people get caught by, replication is not a backup. Replication protects you if a machine fails, but it faithfully copies your data mistakes as well. If you accidentally delete data, every replica deletes it too. So, you need real backups taken regularly that let you restore to any earlier point in time. Now, but replication makes copies. Every copy still holds the whole dataset. So what happens when the data is simply too big or the writes are too many for any single machine to hold? For that, we split the data itself, and that is sharding. Okay, replication copied the whole database, but sometimes the data is just too large to fit on one machine at all. Or there are too many writes for one leader to handle. So instead of copying the whole thing, we split it. Each machine holds only a part of the data. This is called sharding, also known as partitioning, and it is a favorite interview topic. The idea, you take your data and divide it across multiple databases called shards, where each shard holds a different subset of the rows. For example, users with names starting A to H on shard 1, I to P on shard 2, and so on. And the crucial decision is the shard key, the piece of the data you use to decide which shard a row goes to, like the user ID. A good shard key spreads the data evenly, a bad one piles everyone onto one shard. There are two main ways to split: range based, like the A to H example, by ranges, and hash based. You run the key through a hash function to get a number, and that number decides the shard. And since we will use this word a few more times, a hash function at high level is just a function that takes any input, let's say a user ID, and turns it into a fixed number. And two properties makes it useful here. One, the same input always gives you the same number, so you can always find that row again later. And two, the numbers come out spread evenly, so your rows land across all the shards roughly equally instead of piling onto one. Now, here is the hard part, and it is the bit worth actually understanding. The naive hash approach is take the ID, do ID mod the number of shards. That works fine until you add a new shard, because now the number of shards changed, so almost every key maps to a different shard than before, and you had to physically move nearly all your data. That is a disaster, and the classic fix is called consistent hashing. The idea at high level, you arrange the shards in a circle or ring, and each key falls at a point on that ring and belongs to the next shard clockwise. And how does a key fall at a point? You hash it, and that number is its position on the circle. And you hash each shard's name as well. So the shards sit at their own points on the same circle. Now, here is the beauty. When you add a new shard, it lands at one point and it takes over only the keys sitting just before it. Every other key looks clockwise, sees the same shard it saw yesterday, and it does not move at all. This is a whole difference from the modern approach where changing the number change the answer for every key. That is why consistent hashing is such a famous important idea. And there is a common refinement worth naming: virtual nodes, where each real shard is placed at many points around the ring instead of one, which spreads the load more evenly and smooths things out when a shard joins or leaves. And one problem to name: hot shards. If one particular value is extremely popular, say one celebrity user, the shard holding them gets far more traffic than the others. So a good shard key also avoids these hotspots. So, in our store, sharding lets us grow past the size of any single machine, and consistent hashing lets us add capacity without moving all our data. Now, once your data is spread and copied across many machines, a deep question appears. Can all these copies always agree and stay available at the same time? That question has a famous answer, and that is our next topic, the cap theorem. Okay, so now our data lays on many machines, copied and split, and this raises one of the most famous ideas in all of system design, the cap theorem. It is three letters. C is consistency, every read sees the latest data, everyone agrees. A is availability, every request gets a response, the system is always up. And P is partition tolerance, the system keeps working even if the network breaks between the machines. Now, you will often hear the theorem stated as pick two of three, and honestly, that framing is a little misleading, and interviewers like when you know why. You do not really get to give a partition tolerance because the network will break sometimes, whether you like it or not. So, the real situation is this: in a distributed system, when a network partition happens, meaning the machines temporarily cannot talk to each other, you are forced to choose between just two of them, consistency or availability. And since network failures are unavoidable, the network will break sometimes. Partition tolerance is not really optional. So, the real choice in that moment is between C and A, consistency or availability. Let's make that concrete because that is the part that actually matters. Imagine the network splits and a request comes in. You have two options. Option 1, you refuse to answer unless you are sure you have the latest data. That keeps you consistent, but you just become unavailable for that request. That is what a bank does. It would rather show you an error than a wrong balance. Option 2, you answer anyway with the whatever data you have, which might be slightly old. That keeps you available, but you just gave up perfect consistency. That is what a social media feed does. Showing a like count that is a few seconds old is completely fine, as long as it always loads. And this connects to two words you will use constantly. Strong consistency means the moment you write something, everyone sees the new value immediately. Safe but slower and harder to keep available. Eventual consistency means the copies will all agree eventually. But for a brief moment, some might be stale, much easier to scale and keep available. So, money and orders want strong consistency. Likes, views, and feeds are happy with eventual. Picking the right one per feature is exactly the kind of thinking interviews look for. And there is a small extension called PACELC worth naming. Even when there is no partition, you still trade off latency versus consistency. So, in our store, we use strong consistency for orders and payments, and we happily accept eventual consistency for things like product view counts. And that closes part 3. We have now scaled the core system across many machines, many servers, many database copies, split many ways. In the final part, part 4, we cover everything that turns into one real production system: message queues, microservices, the reliability patterns, deployment, and security. See you in the last one.